This video is part of a series of videos on current electricity. In this one, we are just going to look at circuit diagrams, current and charge, charge carriers, as well as drift speed of charge carriers. Without much further ado, let's start. Now, circuit diagrams, you know these because you cover this at IGCSE level, so it should be easy for you. Open switch, close switch, lamp, cell, battery, voltmeter, resistor, fuse, ammeter, light dependent resistor, arrows are coming in, thermistor, just a line which becomes horizontal, variable resistor is an arrow, so don't confuse these two. And then we've got a diode. Remember, forward bias is from right to left in this case. Right, moving on, current and charge. Current is defined as the rate of flow of charge, or just the charge flow per second. For a steady current in a circuit, the charge passed is equal to Q, which is equal to IT, that is in time t. Q is the charge measured in coulombs, I is current measured in amperes. The short form is A, capital A please, not amp, and the time measured in seconds. The coulomb is defined in terms of the ampere, that is 1 coulomb is the amount of charge that passes a point when a current of 1 ampere flows per second. So you lay down the formula, Q is equal to IT, and then you say the charge that flows when a current of 1 ampere flows in a time of 1 second. That is, you are defining 1 coulomb. Do not say 1 coulomb is the unit of charge. No, you have to answer it in terms of what's on the formula. The ampere is a base unit defined in terms of the force on a conductor. 1 ampere is the current in two infinitely long straight wires 1 meter apart in a vacuum, which produces a force of 2 times 10 to the power of minus 7 newtons per meter on each wire. Right, charge carriers. In metals, charge is carried by free electrons. Copper is a good conductor because there are about 1 times 10 to the power of 20 free electrons per cubic millimeter. When a battery is connected to a copper wire, the free electrons are repelled by the negative terminal and attracted to the positive terminal. In a spark, and when lightning occurs, air becomes ionized. The charge is carried by positive ions and electrons moving in opposite directions. During the electrolysis of copper sulfate solution with copper electrodes, charge is carried by positive copper ions and negative sulfate ions in the solution. In a thermionic tube, e.g. a Maltese cross tube, the beam of moving electrons from the cathode to the anode is an electric current. And then in a fluorescent tube, the charge carriers are ions and electrons. Now moving on to charge particles. Electrons carry a charge of minus 1.6 times 10 to the power of minus 19 coulombs. Protons carry a charge of plus 1.6 times 10 to the power of minus 19 coulombs. Now the size of the charge is known as the elementary charge. So it means the elementary charge is E, electrons have a charge of minus E, protons have a charge of plus E. Moving on. Right, charge carriers. Charge is said to be quantized because it can only exist in integer multiples of the elementary charge E, i.e. it can only exist as E plus or minus E plus or minus 2E plus or minus 3E plus or minus 4E, etc., etc. It cannot exist as 2.5E or 2.6E or 1.7E. It's integer multiples of the elementary charge. That's what is meant by the term charge is quantized. Now, the last thing to talk about is drift velocity, and I is equal to NAVE, NAVE. The free electrons in the metal repeatedly collide with one another and with the metal ions in response to the electric field set up by connecting the wire to a battery. They acquire a drift velocity which is about 10 to the minus 4 meters per second, a small drift speed. Now I want to derive this I is equal to NAVE, NAVE. Now we suppose a wire is cylindrical, so inside the wire we do have these charge carriers which we're going to call electrons in this case. Right, so these charges are going to drift when a when a potential difference is set up in between the wire. Suppose the cross-sectional area of the wire is A and the length of the conductor is L. L is equal to speed times time, which is Vt. So we want to find this drift velocity V in the amount of time t. So the mean displacement per unit time is the drift velocity when the PD is applied across the material. The diagram shows an electron moving through a section of wire of cross-sectional area A and length L. So this electron and all these are the electrons. The average time taken T for each charge carrier to move through is T is equal to distance over velocity, which is L over V. If there are n electrons per unit volume, which means that the number of electrons will be equal to that n times the volume. Remember, number per unit volume, you want to change that to number, we just multiply by volume. So it will be n times area times length, so that's volume. The total charge is equal to the charge on one electron times the number of electrons, so which is that Q is equal to N times the volume to get the number, then times the charge on each electron, which is the elementary charge E. The current through the section will be equal to Q over T from our definition, which is going to be equal to that total charge divided by the time, which is L over V. Now if you simplify that, you come up to I is equal to NAVE, or I is equal to NAVE. Now let's look at the example. Estimate the drift velocity of conduction electrons in a copper wire of diameter 0.4 millimeters when a current of 2.0 amps passes through it. Assume copper contains 10 to the power of 29 electrons per cubic meter. And the answer is supposed to be 0.1 millimeters per second. Please work it out and then let me know in the comments whether you get that answer. I'm just going to give you the hint to go about it. Since we want to find V, you make V the subject of the formula here. So V will be equal to I over NAE, I over NAE. Right? I is given is 2.0 amps. N is the number per unit volume, which is 10 to the power of 29. Right? 10 to the power of 29. Now these are in cubic meters, please. So which means you need to convert this to meters, which is 0.4 times 10 to the power of minus 3. And then use to get the cross-sectional area pi d squared over 4. So pi times this squared over 4. And then E is 1.6 times 10 to the power of minus 19. Please let me know in the comments if you have managed to work it out to get this 0.1 millimeters per second. So it means that you need to convert whatever answer you get to millimeters per second to check with this answer. Now to investigate this the movement of ions to cause this drift velocity of charged particles, we perform this experiment that is shown here. Now in this experiment we do have a positive electrode and a negative electrode there, so you don't apply any voltage there, so it becomes negative with respect to this one. So we expect negative charges to drift towards this positive electrode and positive charges to drift towards this negative electrode. Now this is a filter paper shown in white. So this filter paper has been dampened in ammonia solution, aqueous ammonia. And then we've got crystals of copper 2 sulfate as well as potassium permanganate placed right in the middle there. So since this has been dampened, remember the reaction between the copper 2 plus ions and aqueous ammonia form a blue precipitate which dissolves in excess ammonia to give a deep blue solution. This is for chemists. You've got to know your qualitative analysis. I believe you covered this at IGCSE. So the deep blue solution is seen to migrate towards the negative. And then having the copper 2 plus copper 2 sulfate solution, you're going to have copper 2 plus ions. Yes, copper 2 plus ions are the ones that, it dissolves in excess to get that deep blue solution which moves towards the negative electrode. Now the potassium permanganate, it's going also to ionize to form the permanganate ion, which is MnO4 minus, and then it's going to drift towards the positive, like that. So let me just go over the explanation on the notes here. The filter paper is dampened with ammonia solution. Like I said, tiny crystals of copper sulfate and potassium permanganate are placed on the wet paper. A blob of dark blue color slowly sprays towards the negative electrode. A blob of purple color sprays the other way. There is color from the copper sulfate because with the ammonia it forms the positive copramonium ions, which are copper 2 plus complexed with ammonia. Which color the solution is deep blue. There is a color from the potassium permanganate because it forms negative negative permanganate ions, MnO4 minus. Which color the solution purple. The positive ions move one way and the negative ions move the other way. The drift speed is remarkably very low, perhaps millimeter per minute, 1 millimeter per minute or less. So the drift velocity is similar to the drift velocity of the electrons in a metal. So I want to show this in a video so that you see the experiment. Let's see if I can show it. Right, so there you are. You do have the two copper 2 sulfate there, and then we have the KMnO4, which they are now. So they've already put the copper sulfate there, and then they've dampened this filter paper, and then we've got a positive electrode there and a negative electrode there. Now placing the potassium permanganate onto the filter paper and see what's going to happen. Right, putting the potassium permanganate back. Now after some time you see that there is a purple solution moving towards the positive, right? Purple solution moving towards the positive here. So these are the MnO4 minus ions, permanganate ions. And then the copper 2 plus slowly changing color to the deep blue color and migrating towards the negative, which will be this side here. Let's just watch for a few minutes and then we draw a conclusion. So here we can see the purple color developing nicely. Yeah. The blue color is also developing here nicely, vividly. Yes, we have more blue color accumulating there. It happens very slowly. Remember, we calculated this drift speed times 10 to the power of minus 4 meters per second. So it's very, very slow. Yes, but it is developing nicely, as you can see. Right, so after some time, this is what we get. We get the deep blue solution going like that. It's slightly changed from the color that we had here. Okay, so there we are. So we have shown the deep blue. We've shown the drift velocity of electrons in this experiment. So please let me know in the comments if you want further clarification on any part of this topic that I was looking at. Signing out.